Alrighty, folks, we're going to start here with the next lesson of Chapter 3. We've introduced Newton's second law in the previous lesson, but now we're really going to do a lot more examples focused on it, where we mostly focused on examples of the first law in the previous lesson. Just a reminder, as always, make sure you are following along actively, right? Taking your own notes so that you're engaging and getting the most possible out of this lesson. All right, here we go. Let's start out by reminding ourselves of what Newton's second law actually says. And honestly, the second law is best stated, I think, as the equation, right? It just says that if an object is experiencing a net force, it will accelerate, and that acceleration will be equal to the net force it's feeling divided by its mass. So it will accelerate. Its velocity will change, okay? And more than that, it also tells us how the acceleration will depend on, well, two things, right? The net force, so how hard it's actually being pushed overall, right? And the equation shows us that. F net is in the numerator here. So if we have a bigger net force, we get a bigger acceleration, which again, you've known for a long time, even before you took a physics class, right? If you want to change something's motion more, you need to push it harder with a bigger force. And it also, we can see it depends on the mass of the object, okay? But that is an inverse relationship where a larger mass results in a smaller acceleration. In other words, if you push something bigger with the same force, it won't accelerate as much as a smaller thing. And again, you knew this, right? If you push a truck with the same force as you push a bicycle, the bicycle is going to change its motion a lot more than the truck will, which once again shows up in the equation. We're dividing by the object's mass, so a larger mass, we're dividing by a bigger number, gives us a smaller acceleration as a result. Okay, so again, reminder on terminology there. Directly proportional means when one gets bigger, so does the other. That's the relationship. A bigger net force results in a bigger acceleration. Inversely proportional means the opposite. When one gets bigger, the other gets smaller. So a larger mass results in a smaller acceleration. Symbolically, we represent these proportionalities like this. We say acceleration is proportional to the net force, right? Again, it's not saying acceleration equals the net force. It's just saying this is how acceleration depends on the net force. If we make this bigger, this gets bigger too. And an inverse relationship is shown like this. We say acceleration is proportional to the inverse of mass. In other words, if mass gets larger, acceleration should get smaller. We're dividing by mass. But that's Newton's second law. It's this equation, right? It tells us that an object will accelerate if there's a net unbalanced force, right? And it also tells us how it will accelerate based on the force and the mass it's acting on. Reminder, this is actually this tells us Newton's first law as well, because if F net were 0, well then the acceleration would be 0. And that's Newton's first law. If no net force acts on an object, it will not accelerate. It will keep doing what it was doing. If it was sitting still, it'll stay sitting still. If it was moving at some velocity, it will continue to move at that same velocity. That was Newton's first law. It's kind of cooked into the equation of Newton's second law. So from our formula sheet, if we use Newton's second law to answer a question, we are applying physics principle number 1, okay? And we're just going to be using this equation here. This really is the equation we will use for all of Unit B. Pretty much every question will be solved with that equation in some way or another. So physics principle number 1 on our formula sheet. Okay, now important reminder, F net is not just a force, right? It's the net force, like the resultant force. It's the total force that's acting on an object once you've considered and added them all together, right? Following our usual rules of vector addition. So it is a vector, it has a magnitude, a direction, and it can have components in both the x and y axes. We'll have to be considerate of all of that stuff. So we looked at this a bit in the previous lesson, but now that we're really diving into Newton's second law examples, let's revisit some visuals here, okay? I've paused time right now. I've turned it so that there is no friction, okay? And I'm going to be applying a force to the right, okay? Now, the sum of all of the forces acting on it, since there's nothing else going on, the total net force is to the right. And so sure enough, our object accelerates, right? It is picking up speed. You can see the speedometer up there getting faster and faster. It is accelerating, okay? If I take away that force, it stops accelerating but continues moving. Now we're looking at Newton's first law again. Okay, but let's explore what happens when I use a larger force. The equation tells us we should get a larger acceleration, so its velocity should change more each second. Let's see what happens. I'm now applying 200 newtons of force instead of only 50. And sure enough, we can tell, right? Look at how quickly its velocity is increasing. It has a much larger acceleration because there's a greater net force on it. All right, but what about mass? So I'm going to keep the same applied force, still 200 newtons, okay? But I'm going to make this thing a lot heavier. Oh, okay, there we go, sure. Now he's pushing a much heavier object, right? So same force, but a much heavier object. Let's see what happens to the acceleration. Sure enough, much slower, right? Still accelerating because there is still a net force, but you can see that acceleration is much smaller. Acceleration equals net force acting on the object divided by that object's mass. Okay, now it's important to remember accelerations are not just speeding up, right? So I'm going to show something here. I'm going to let this go. Now notice there is a net force. It's the force of friction. And our object is accelerating. Remember, slowing down is an acceleration. It's your velocity changing. It's just changing in such a way that it's getting slower. The acceleration is in the opposite direction of the velocity, okay? So let's watch what happens here, right? Remember, it's not just a force that determines the acceleration, it's the net force. So notice, even though I'm applying a 200 Newton force here, we're not accelerating as much as we were when we had no friction, because the friction is canceling out with that applied force. You can see the sum of forces there is smaller. And then once again, once I let it go, there's no longer an applied force. So the net force is just friction, and it continues to accelerate, but now it's actually accelerating in the opposite direction because the net force is just the friction, which is in the opposite direction of how I was pushing it, right? If I push it again, I can make it accelerate to the right. If I let it go, the net force is now to the left. It's just friction, and so it accelerates to the left, gets slower and slower and slower, until eventually friction should bring it to a stop. Wait. And there we go. And now because it's no longer moving, there's no friction. Friction happens when objects move past each other or try to move past each other. Since there's no net force, it sits at rest. It's no longer accelerating. Okay, so let's try some very basic examples to kind of introduce ourselves to the equation a bit here. So we have a 19.1 kilogram curling stone. So that's our mass. Remember, we measure masses in kilograms, not grams. Curling stone decelerates. Okay, so deceleration, remember, that is an acceleration. It's just an acceleration where the velocity is changing in such a way as to get slower, right? Any change in velocity, whether it makes you faster or slower, is an acceleration. So all that means is that if our curling stone is moving, say to the right, the way I've drawn it, right? Its velocity is that way. Its acceleration is in the opposite direction. Okay, I'm going to go ahead and define the direction of the acceleration as positive. Okay, just because that way I'll have more positives makes the math easier. So I'm going to make it positive 0.100 meters per second squared. Essentially, I'm making backwards for the curling stone positive, right? You could make it negative. You'd get the same result. Your signs would just be flipped. We want to determine the net force during its acceleration. So what was the net force acting on this stone? That net force, by the way, looks like it would probably mostly just be friction because we've let it go. We're not pushing it anymore. So the net force in this case, the sum of all the forces, it looks like the only force really acting on it in this situation would be friction. So we can just apply physics principle number 1 here, right? Which is essentially just this equation. The acceleration will be equal to the net force divided by the mass. We want to find the net force, so multiply both sides by mass. And we're ready to plug in our numbers and solve. Everything is already in the correct units, so life's good. Going to put in a positive because I'm defining the direction of the deceleration as positive. And we get that The net force would be 1.91. Okay, now kilograms meters per second squared. Those are the base units, but remember, we give that the name newtons because we use forces so much we get sick of calling them kilogram meters per second squared. Okay, I got a positive, which means it's accelerating. The net force is in the same direction as the acceleration because we called that acceleration the positive direction. So that makes sense. If we want, we could say, backwards or against the rock's motion for our direction, but there we go. So to fill this in, we would do 1.91 newtons. On a Scantron or in Smarter Marks, we would do 1 and then a decimal in the second box and then a 9 and a 1. All right, a 1,700 kilogram car accelerates when it reaches the highway. So we know that F net will not equal 0 because it's accelerating. Its engine applies a force of 2,500 newtons forward, while the force of friction acting on the car is 1,000 newtons backwards. We want to figure out what is the acceleration of the car. Okay, let's draw some diagrams to get our bearings here. So the engine applies a force of 2,500 newtons forwards. So the engine applies a force of 2,500 newtons forwards, so we'll call that Fe for engine. And the force of friction is 1,000 newtons backwards. So smaller, but backwards, against motion. That makes sense. Friction is always against motion. Now I got to be super careful, right? These are vectors. Vectors in opposite directions need opposite signs. So I'm going to call this negative 1,000 newtons because I'm going to define forwards as forwards as positive and therefore backwards is negative. If we draw a free body diagram here, right, we can see that yes, this thing should be accelerating because the force of the engine forwards is larger than the force of friction backwards. So they're not quite going to cancel each other out. There will be a net force. If you wanted to, you could also include that there's a normal force from the road upwards and a force of gravity pulling the car downwards. Truth be told, in these types of scenarios, we can kind of see since it's all horizontal, we don't necessarily have to worry about those as much, but not wrong to include them by any stretch, okay? In later lessons, in later problems, it will be important to also think about what's going on there because it might not just be that case where they perfectly cancel each other out and we can kind of tell that from the get-go. And for our vector addition diagram, I'll just do it horizontally so we can see, right? Again, the vertical stuff, not as important for this question. We can tell that vertically they're just balanced out. But sure enough, force of the engine forwards, force of friction backwards does leave us with a net force forwards. So it should be accelerating, right? And we know that the acceleration will just be equal to the net force divided by the mass. And since this is all happening horizontally, we could even say the acceleration in the x-axis will equal F net x divided by the mass, right? Which is always true, but in this case, that's where all of the acceleration is happening because in the y-axis, there's no net force. So what is F net x? Well, it's the sum of all our forces in the x-axis, right? We just have the engine and friction to consider here. So Fe plus Ff divided by the mass of the car will give us the car's acceleration. That's it. F net x is the sum of all forces in the x-axis. The net force is the sum of all forces. So we just need to add these two forces. Well, the engine is 2,500 newtons forward, and the force of friction is 1,000 newtons backwards. So I'm going to put that in as negative 1,000 newtons, and then we divide by the mass of the car, which is 1,700 kilograms. So that gives us this, right? 2,500 minus 1,000 leaves us with 1,500 newtons. That is the net force acting on the car. Yes, the engine is pushing with 2,500 newtons forward, but 1,000 newtons of that is just used to fight friction. Friction cancels it out. So I got that the acceleration of this car would be 0.88235 meters per second squared. Now, I got a positive. Does that make sense? Should we have gotten a positive? Well, yeah, because we defined, right, the direction the engine was pushing forwards as positive. And we knew that the engine was stronger than the friction, so the net force overall was forwards, and therefore it should be accelerating forwards. Okay, so I actually get 4 significant digits here. To 4 significant digits, 0.8824 meters per second squared. And don't forget, acceleration is a vector, and we can actually say what positive means here. It means forward. There we go. Last introductory example here, we want to determine the net force needed to accelerate a 1,000 kilogram car from 0 to 2 kilometers per hour left in 45 seconds. Okay, so they didn't directly tell us the acceleration here, right? If they did, we could just do A equals F net over M and solve for F net. However, right, when in physics, sometimes they might not give us exactly what we need, so we can either give up or we can say, okay, can I find what I need? So what did they give us? They said it's going to start from 0. Well, that's its initial velocity, right? And we want it to end up at this velocity. That's its final velocity. And they also gave us the time. So if we list out our givens here, of course, we'll need to convert these kilometers per hour into meters per second. So every kilometer is 1,000 meters. And then we don't want meters per hour, we want meters per just 1 second. So we'll need to divide by 3,600, right? Can check that our units are canceling out correctly, but 1 hour is 3,600 seconds. And that gives us that 2 kilometers per hour is 0.5 repeating meters per second. Remember, we're not going to round that too much because we don't want to over-round and end up changing our final answer. Okay, we also know that the time we want it to do this acceleration in is 45 seconds. Okay, and ultimately we want to figure out F net. And again, we have the mass, we want to know the net force. If we just had the acceleration, we'd be good to go. But look, we do have the initial velocity and we do have the final velocity, so we can use those to figure out how much its velocity changed by, and we also know how long it needs to take to complete that change in velocity. Well, hang on a sec, that's just how we, would have found the acceleration in previous units and in previous courses. It's actually like the definition of acceleration. How much did its velocity change per second? So there we go. We might not have been given acceleration directly, but we definitely have what we need to find it. So the acceleration is the change in velocity divided by time, and therefore final velocity minus initial velocity, which is just the change in velocity. So putting in our numbers, but first I should definitely define my directions. I'm going to call, since everything here is to the left, I'm actually going to make that positive and right negative. And that way, I don't have to introduce a whole bunch of negatives into my equation. So making left positive, I have final velocity of this minus initial velocity of 0 divided by, it completed that change in velocity in 45 seconds, giving me that the acceleration during that time was 0.012346 meters per second squared. Okay, so now with that acceleration, right, we can find the net force because we know the mass and we know how much it accelerated by. Acceleration equals net force divided by mass, so multiply both sides to find that F net equals ma. That's often our starting point for these. F net equals ma, so F net equals 1,000 kilograms times an acceleration of 0.012346 meters per second squared. And I get that F net must have been positive 12.346 newtons. Okay, positive. Is that a good sign or a bad sign? That's a good sign because we knew it was accelerating to the left and we called left positive. Well, to accelerate to the left, you need a net force to the left. So it's a good thing we got a positive. We were expecting a positive. So to 2 significant digits, the net force acting on the car must have been 12 newtons, and force is a vector. So 12 newtons to the left. All right, so your turn. Pause the video. Try this one out for sure, okay, before continuing on. And if you're feeling like you want a little more practice with these, basic F net equals ma type calculations, these are a good practice for that as well before moving on. But you can wait until the end and do those with the rest of your practice if you'd like. No matter what, though, make sure you try this one out. Okay. So let's think about, explaining some stuff with Newton's second law. So why does catching a gently tossed baseball not hurt your hand, but catching a fastball thrown by a big league pitcher would seriously hurt your hand? Well, let's think about what's the same and what's different in both situations, right? In both situations, you catch the ball, so you stop it. So either way, the final velocity is 0. Now, for the gentle toss, before you caught it, it was traveling through the air with some velocity, right? We can call that its initial velocity, the velocity it had before you caught it, okay? Now, compared to the fastball, that initial velocity for the gentle toss is a lot smaller, right? VI is small for the gentle toss and very large for the fastball. So think about what that means for the change in velocity, right? If they both have the same final velocity, and this started with a small initial velocity, then the change in velocity, VF minus VI, is going to be small for the gentle toss compared to the fastball, right? If V final is larger, if V initial is larger and V final is 0 either way, then this one is going to have a larger change in velocity. Okay, now a larger change in velocity means a larger acceleration needed to occur, right? Assuming it took you the same amount of time to catch it, which it would either way, right? You're just sticking your hand out and catching it. So since the gently tossed ball has a smaller change in velocity, that requires a smaller acceleration, right? And vice versa. The fastball has to go through a very large change in velocity and therefore needs a larger acceleration. Now, what's causing the acceleration? Right? You catching it, and we know that that's a force, right? An acceleration can't happen without a force. So you are exerting a force on the baseball in order to bring it to a stop. And forces are what we feel, right? Forces are what hurt us, right? When you push on yourself lightly, it doesn't hurt. But if you push on yourself really hard, right, with a larger force, it can start to hurt. And so what requires a bigger force? A small acceleration or a big acceleration? Right, the big acceleration. So since we have a larger acceleration here, that's going to involve a larger force of you on the baseball and therefore of the baseball back on you. So since the gently tossed ball requires a much smaller acceleration to bring it to a stop, the forces involved are also much smaller and therefore don't hurt you that much. But with the fastball, it's a very large acceleration requiring a very large force, and that force is going to be enough to hurt you. So while we're on the topic, I want you to think about this situation, okay? In both, we have two different types of ball. A bowling ball that's moving at 10 meters per second, and a ping pong ball that's also moving at 10 meters per second. Which one of these is going to hurt more? Now, you know the answer, but can you explain why with what we know about Newton's second law? I want you to pause the video and take a second and think about it, right? Use the equation to think about it and remember that forces are what hurt us, right? Okay, well, take a look here. The acceleration either way, if this hits us and comes to a stop versus if this ping pong ball hits us and comes to a stop, right? Either way, the acceleration was the same because it went from the same initial velocity to the same final velocity of 0, right? So what's the difference here? It's the mass, right? A much bigger mass is going to take a much bigger force to accelerate. And therefore, that force is, you're applying it to the ball is applying it to you. That's going to hurt. Forces hurt, right? Big forces hurt more, okay? Versus, over on this side, a much smaller mass for our ping pong ball requires a much smaller force to accelerate the same amount. And so the ping pong ball doesn't hurt as much. Okay, so let's think more about this relationship again between the net force and the acceleration, especially when there is more than one force contributing to the net force, okay? So we want to draw free body and VAD diagrams for each of the following. First up, a hovering helicopter. Okay, so if it is hovering, is it accelerating? No, right? It's just staying still. So the acceleration is 0, and therefore, what is the net force? Also 0, right? So what do we know about the forces? They need to cancel each other out. If there's multiple forces, they're balanced, okay? So for our free body and vector addition diagrams, that's the type of thing we're thinking about, right? Is it accelerating? No. So the net force is 0. Doesn't mean there's no forces acting on it, just means they cancel each other out. That's always one of the first things you should ask yourself when dealing with any dynamics problem, right? Is the net force going to be 0 or not 0? Because then you know what generally should be going on with them canceling or not canceling and how big they should be. So a hovering helicopter definitely has mass, so it's feeling a force of gravity downwards, right? But for it to stay hovering, something must be pushing up just as much. And in the case of a helicopter, we would call that force lift, usually, F lift, or you might even call it thrust. Okay, so for our free body diagram, we represent the helicopter just as a dot, and then however much the force of gravity is pulling downwards, thrust or lift needs to be pulling up. I'm just going to say TH for thrust. Now for our VAD, right, we're expecting these to cancel out. So the force of gravity down, tip to tail with the force of thrust upwards. Sure enough, they're just as big as each other. To draw the net vector, there's nothing to draw because it starts where it begins. And the net force is 0. What we'd expect for a helicopter that's hovering, not accelerating. So now a person with a jetpack is accelerating up slowly. So what do we know about the forces? 0, net force 0 or not 0? Not 0, right? The acceleration is not 0, so the net force cannot be 0 either, right? There needs to be some net force. And what's more, we know that it needs to be, which direction is the net force? Right, up. Something can only accelerate up if there is an upward net force. So again, a person with a jetpack is going to have mass. They're going to feel a force of gravity downwards, okay? But the thrust from the jetpack is providing an upwards force that is bigger than that force of gravity, okay? Now, I didn't draw it way, way bigger. Why do you think I only drew it a little bit bigger? Right, because it's accelerating up slowly. And a slow, small acceleration, right, comes from a small net force. So there is a net force upwards, but it's not very big. If we draw our vector addition diagram here, force of gravity is downwards, and the force of thrust is bigger, but not like dramatically bigger, right? Maybe that big. To provide, yes, an upwards net force from where we started to where we finished, there is a net force upwards, but it's not huge because our acceleration is not huge. Now, what do you think I'm going to do differently for this one, where we have a rocket that has a very large upward acceleration? So there's still going to be a net force upwards, right? But it's going to be bigger than it was in example B, right? So for our free body diagram, I'm going to give myself some room here. Rocket still has mass, still feels a force of gravity, but now the force of thrust from that rocket is not only canceling out the force of gravity, it's canceling out with a lot left over, so that there is a very large net force upwards to provide that very large upwards acceleration, right? Look at our net force now. From where we started our diagram to where we finished, that's a much bigger net force upwards, which is required to provide a much bigger upwards acceleration. Alrighty, let's try out one where we actually have to make a calculation now. So a 50,000 kilogram rocket accelerates upwards at 1.2 meters per second squared. What is the force applied by the thrusters? So we're looking for the force that is applied upwards by the thrusters. So the rocket has mass. We know it's mass, right? So it's going to feel a force of gravity. And in fact, we basically have the force of gravity because remember, the gravitational force acting on an object is equal to mass times acceleration due to gravity. G, 9.81 meters per second squared on Earth. Now it's accelerating upwards, so the net force is not 0. That upwards thrust must be larger than that downwards force of gravity. Okay, so here's our equation, right? Like I said, this equation is pretty much going to get us through all of Unit B. The acceleration of an object will be equal to the net force acting on it divided by its mass. And therefore, F net is equal to mass times acceleration, right? F net equals ma. And what is F net? Well, F net is just the sum of all forces, right? So in this case, everything's in the y-axis. We can just go ahead and add them up as long as we're careful to define our positive and our negative directions, right? So I'm going to call up positive, down negative. So what contributes to F net here? Well, we've just got the thrust upwards and the force of gravity downwards. So let's break this down. F net is really just F thrust plus the force of gravity. And that equals mass times acceleration for the rocket. All right, now we are trying to solve for F thrust, right? Right now it's having Fg added to it. So if we subtract Fg from both sides, we get this, right? The thrust is mass times acceleration minus the force of gravity. And we know that the force of gravity is just the rocket's mass times 9.81, acceleration due to gravity. So the thrust must be ma minus mg. Okay, so coming up here, if we put in all of those numbers, because we know the mass of the rocket, we know its acceleration, and we know acceleration due to gravity is 9.81, we can put in our numbers and solve. We just need to be very careful about our signs, right? So F thrust will be 50,000 kilograms times this upwards acceleration of 1.2 meters per second squared. I'm calling up positive, so that's a positive acceleration, minus mg. So the rocket's mass is still 50,000 kilograms, but acceleration due to gravity accelerates you downwards. So that is negative 9.81 meters per second squared. Okay, we have all those numbers. We can put them in and calculate out. Be very careful with negatives, right? We're subtracting a negative here. Don't want to miss that on your calculator. But when I did that, I got that the force of thrust must have been positive 550,500 newtons. Okay, so we can check our work a little bit here. Positive, good. We knew the thrust had to be upwards, right? Not only did it have to beat out gravity downwards, it also had to overcome it by a bit to still provide a net upwards force and acceleration. Okay, so let's just do significant digits and directions here. We only get 2 significant digits, so we'll definitely need scientific notation. We need to move the decimal once, twice, 3, 4, 5 times. So we're going to have to 2 significant digits, 5.5 times 10 to the power of positive 5 newtons, and the direction would be upwards. There we go, right? So again, did we get a fancy formula going on eventually? Sure, yeah, our equation got more complicated, but we started with the basic idea, as we're going to do on any problem we solve in physics. We take a simple starting principle, right, and then we get specific to our question. F net equals ma. In this case, F net was F thrust plus Fg, right? And from there we went. Okay, let's look at some examples involving elevators. These are kind of a classic type. And the reason is they're a nice way to think about Newton's second law because they're nice and simple since everything is confined to the y-axis, right? Elevators, well, at least most elevators, should only move up and down. We don't need to think about horizontal, right? So we only need to consider the force of gravity pulling downwards and some upwards force, okay? Today we're going to look at the forces on the elevator itself, okay? Which means we're usually thinking about tension in the cable. So we're looking at the whole elevator. It has mass, so it feels a force of gravity downwards, but there's some cable attached with a force of tension in the cable that's pulling up on the elevator. Later in this unit, not really in this lesson, but when we start talking about apparent weight, we're going to be interested in not the forces on the whole elevator, but the rider of the elevator specifically. And it's all the same principles. They're still feeling a force of gravity pulling them downwards, But now the upward force for them, they're not attached to the cable, right? For them, the upwards force is actually the normal force from the floor of the elevator, right? Without that, the elevator doesn't take them up. If an elevator didn't have a floor, it wouldn't work very well because it would just leave without you, right? So that's later. We'll look at the upwards force being the normal force. And again, it's not like the physics is any different there. It's still just upward force, downward force, find the net force to think about acceleration. It's just whether you're interested in the whole elevator, right? Or a specific person in the elevator, what the actual relevant forces are. Okay, so remember, as we head into this, the sign for acceleration is related to direction. It has nothing to do with speeding up or slowing down, right? Sometimes students forget that a negative acceleration doesn't necessarily mean you're getting slower. It just means you're accelerating in the negative direction, okay? So for these examples, we're going to calculate the tension in the cable of a 1,000 kilogram elevator in some different scenarios. So in all of them, we are looking for what the tension would be. So we'll start with the elevator at rest. Now, again, like I said, good first thing to always ask yourself is, what does that mean for the net force? Is it accelerating if it's at rest? No. So is the net force 0 or not 0? It's 0, right? So we've set ourselves up for success by thinking about that, because now we know that whatever forces are present, they need to be canceling each other out, right? So there is a force of gravity downwards pulling the elevator down, but tension in the cable pulling it up must be just as large. Opposite direction, but same size. Okay, so we could start here. We could just say F net equals 0, right? And then say, all right, well, what is F net? It's all in the y-axis, so we can say Ft plus Fg equals 0 and solve for F tension. But we can also start even more general and say F net equals Ma, right? And then recognize that, oh, A is 0, and we get to the same place, right? We get that F net equals 0. So I'm just pointing out there that Newton's first and second laws are quite closely connected, right? F net equals Ma becomes Newton's first law if A is 0. So I'll go with this for now, right? We want to solve for the tension. Okay, so subtract Fg from both sides, and we get that Ft equals negative Fg. Hey, the physics is speaking to us through the math here, right? We said that tension had to be just as big as the force of gravity, but in the opposite direction, up instead of down. Well, look at this. The force of tension has to equal the force of gravity, but in the opposite direction, opposite sign, right? Now, force of gravity, again, as long as we know the mass, we can calculate that, right? It's just mass times acceleration due to gravity, or 9.81. So we're good to go, right? We know the mass, it's 1,000 kilograms, and we know acceleration due to gravity, so we can calculate Ft. Now, before I do that, I'm going to define up as positive, down as negative, and we're good to put in our numbers. Mass is 1,000 kilograms. And acceleration due to gravity, gravity accelerates you downwards, so negative 9.81 meters per second squared, to get that our tension is negative, so positive 9,810 newtons. That positive means up, like we would expect for this tension, right? Now, I did use 9.81, so my answer should have 3 sig digs here. All right. Now, what if the same elevator is no longer at rest, but moving down at a constant speed of 2 meters per second? Is that elevator accelerating? No, it's not, right? It's not accelerating. It's moving at a constant speed. So its acceleration is still 0, and the net force on it is still 0. Remember, right? Moving is not the same thing as accelerating. Objects can be moving very fast and have a net force of 0, right? That just means they're not changing how they're moving. Not necessarily that they're not moving at all, right? Again, net forces don't necessarily cause motion, they cause changes in motion. So because our acceleration is 0 here and our F net is 0 here, the calculation is actually going to be the exact same, right? Nothing's changed about its mass and its acceleration is still 0. So I can honestly just copy and paste this. My setup would be the exact same. All right, so there we go. I copied and pasted because it will be the exact same. Remember, this is great to know. Nice to know that the speed is 2 meters per second, right? But speeds have nothing to do with the forces. Changes in speed, accelerations are caused by forces, right? So if it's not accelerating, which it's not, if it's moving at a constant speed, then F net is 0 and the tension plus the force of gravity equals 0, right? Rearranging, putting in all the same numbers because nothing's changed there, we get the exact same answer. By the way, this is why you can be moving very, very fast, like say a car on the highway, and like take a nap, right? You can take a nap when a car is going 100 kilometers per hour on the highway, as long as you're the passenger, not the driver, right? Because you might be moving quickly, but you're not accelerating. So there's no net forces acting on you. And so forces are what we feel, remember, right? So you can be sitting in a car going very fast and it doesn't feel that different than sitting at home in your chair as long as you're not changing that velocity. If you're not speeding up, slamming on the brakes, taking sharp turns, right? All of those are accelerations. If you're just going on a flat road at a constant speed, you can take a nap, right? Even in an airplane that goes even faster, right? When it's not changing its velocity, you hardly know the difference between sitting on an airplane and sitting at home on your couch. All right, now things get more interesting. It's moving up, but accelerating down at 2 meters per second squared. So again, ask yourself, is F net 0 or not 0? It is not 0, right. And in which direction is the net force that's not 0? Well, it's got to be down, right? If it's accelerating down, that requires a net force downwards. So we've set ourselves up for success here because now we can think about this, right? We know that the downward force in this tug of war needs to be winning. It needs to be larger. Okay, so the force of gravity didn't change, right? Because the mass of the object didn't change. It's still the same elevator. So a common student mistake here would be to say that, okay, so Fg must have gotten larger for it to accelerate down. But we're kind of locked in with Fg because the mass of our elevator is not changing. So what must have happened then if we have a net downward force? Right, in Ft, the force of tension must be smaller. So now we can't say F net equals 0, but we can always say F net equals mass times acceleration, right? And still, what is F net? Well, it's the sum of all forces, right? And we still just have the same two forces. They're no longer the same size is all that's different. So Ft plus Fg has to equal mass times acceleration. And therefore, our force of tension will equal ma minus Fg. So notice here, when thinking about the forces, did we ever care that it was moving up? No, right? Because again, it's not about how it's moving, it's about how it's changing how it's moving, how it's accelerating. So it's nice to know this, right? But this is what matters when it comes to forces. Forces cause accelerations, okay? Changes in velocities, not velocities, okay? What we can say from this is that now we know it's getting slower. Right? If it's moving up but accelerating down, it is moving up, but it's getting slower and slower and slower. This would be the part of the elevator ride where you are going up to a higher floor and you're starting to reach your destination. So the elevator slows down. So just moving up here where I have a little more room, Fg is still just mg, mass times acceleration due to gravity. Well, we know the mass, we know the acceleration, right? And we know acceleration due to gravity. We can calculate the tension here. Just don't forget, we're going to make that downward acceleration negative. So our elevator is still 1,000 kilograms and it's accelerating down at 2 meters per second squared. So I'll put in a negative minus 1,000 kilograms, and acceleration due to gravity is also negative because it accelerates you downwards. So being very careful with my negatives on my calculator here, right? We're going to have a negative minus another negative, okay? I got that the force of tension would be 7,810 newtons, a positive, so up. Now look at this, right? It's smaller than when the elevator wasn't accelerating, like we predicted, right? Ft is no longer canceling out Fg, it's a little bit smaller. Sure enough, we're getting that the tension is smaller than when tension just equaled Fg. And you can try this out for yourself. If you have something attached to a string, right? Accelerate it downwards and you'll notice the tension, you can feel it in the string, it gets a little bit smaller when it's accelerating downwards. Again, not moving downwards necessarily, accelerating downwards. So you could try this, move it up and then get slower. And when you start to get slower, you'll notice that the tension in the string feels a bit smaller. All right, now moving downwards, but accelerating upwards at 2 meters per second squared. So, pause. Which one of those pieces of information is important for thinking about forces? The moving down or the acceleration up? Right, the acceleration up. Moving down, great to know, but actually tells us nothing about what the forces are, right? You could be moving down and accelerating down. You could be moving down and accelerating up. And the acceleration is what's caused by our net force, okay? So all this lets us say is that it must be getting slower. It's moving down, but it's accelerating up, right? So this would be you get on the elevator to go down now, and you're getting to the bottom towards your destination. So it's starting to slow down by accelerating upwards. So the net force is not zero, and in which direction must the net force be? Well, up. To accelerate up, you need a net force up. So still, the force of gravity can't have changed. Our elevator still has the same mass, and acceleration due to gravity hasn't changed, right? So how do we get a net upward force? The tension must be larger now than it was before. But it's still the same equation to figure that out, right? Again, just F net equals ma is going to get us through most of this unit. Now, F net is just the same as always, the sum of all forces. Can you see how this is a little repetitive here? Well, that's because we're dealing with all the same forces. They're just got different sizes, right? Look, in fact, you might be able to put together that I'm not going to do anything differently for the rest of this calculation except put in different numbers, right? All the same ideas at play here. Okay, so now I'm just going to move where I have more room and we can put in our numbers, being careful about signs. So our elevator is accelerating upwards at 2 meters per second squared. That is a positive acceleration for me, so positive 2 meters per second squared. And gravity always pulls you downwards, so that is a negative 9.81. Putting that in my calculator, being careful about negatives, I got 11,810 newtons. It's positive, so it's up. And once again, look at that. Just like we predicted, it's a little bit bigger than when tension and gravity were just balanced, right? And you can also feel this for yourself. Right? If you have something that is on a string, now accelerate it upwards. So maybe that's going faster up or going down and getting slower at the bottom, okay? You'll notice the tension increases. You can feel it in the string. It gets a little more tense whenever you're accelerating it upwards. All right, last one here. Moving down and accelerating down at 2 meters per second squared. Once again, which one of those is important for thinking about the forces involved? Right, the downward acceleration, okay? In fact, do you think this is going to be any different than this? Number 5, is that going to be any different than number 3? It's not in terms of the forces involved, right? Okay, yes, different scenario. This one's moving up and getting slower. This one's going to be moving down and getting faster, right? But in terms of the forces involved, these are identical because they both have the same downward acceleration. So I'll start the same setup, right? But again, you can see where we're headed. What is F net? Well, Ft plus Fg. And so rearranging that, we get that the tension is ma minus Fg. Fg is mg, right? And nothing is different from example 3 when we go to put in our numbers because the acceleration is 2 meters per second squared downwards, right? Of course, acceleration due to gravity hasn't changed. And so, like we predicted, we get the exact same tension. Because again, it doesn't really matter what direction it's moving for the forces involved. It's about how it's accelerating. All right, let's try a different elevator example here before we shift gears a bit. All right, so an elevator cable can withstand a maximum tension force of 2.5 times 10 to the 4 newtons. If it accelerates upwards at 2.35 meters per second squared, what is the maximum mass that can be lifted by the elevator? So definitely the type of calculation that civil engineers do all the time, right? Or all kinds of engineers and different people involved in manufacturing, right? You want to make sure your elevator is safe, right? So you need to know what type of cable to use to make it safe. So if this is the biggest tension force possible, right? Let's draw our free body diagram. Okay, so there's our tension force. The maximum possible tension force. What we're trying to figure out is how big can the mass be for that to be still safe, right? What's the biggest possible mass where that tension will be okay and the cable won't snap, right? So we're thinking about Fg. Now, it accelerates upwards at 2.35 meters per second squared. So as we just saw, that is, if that's the max acceleration, then this is the biggest the tension will ever get, right? Tension needs to be larger when accelerating upwards to overcome gravity. So the force of gravity is just mass times acceleration due to gravity. What we ultimately want to know is what can that mass be for this scenario to be safe? But it's still going to be, remember what I said? The same equation is going to get us through just about every problem we solve here. Okay, Newton's second law. Acceleration is equal to net force divided by mass, and therefore, the net force, the sum of all the forces, equals mass times acceleration. If you are solving a problem involving forces and you have not written this equation, right, you probably want to rethink your approach, okay? So, what is the sum of all forces here? Well, we've got tension up and the force of gravity down. Whatever those are together, they have to equal the mass times the acceleration. Now, the mass that we want to solve for is there, but keep in mind, right, it's also in here. We don't know the force of gravity because we don't know the mass, but that's what we're trying to figure out. So Ft plus Fg equals ma, but Fg is just mg, mass times 9.81. Now, we want to solve for mass, but it appears twice in our equation. Don't panic. We can solve this. You've done it in previous courses, okay, in math courses, okay? We'd start by first just bringing everything to one side. Bringing all the masses to one side so that we can start getting it isolated. So let's subtract mg from both sides to get now that Ft equals ma minus mg. So remember, we're solving for mass. It's a little bit better because now at least they're all on one side, right? However, it's still not isolated. Now, to do this, we're going to need, okay, to remind ourselves of a skill from math class. Notice this mass and this mass are the same thing, right? It's just the mass of the elevator. So these are the same number, right? Now, if we were in math, and you had something like this, right? You would be okay with, or at least at one time you were okay with, pulling out the 7 as a common factor, right? We have 7x's plus 7y's. We can pull out the 7 as a common factor, which means divide 7x by 7, divide 7y by 7, right? And then multiply by 7 outside. And we can see that that's okay because if I multiply it back in, I'm back to where I started, right? So it's the same idea here. Ft equals ma minus mg. What we can do is pull out that mass as a common factor, a minus g, right? Again, we can see we haven't broken any rules because if I multiplied the mass back in, I'd just be back where I started. So it is equivalent to what we had before. And what that now allows me to do is solve this equation for mass because mass is just being multiplied by a minus g. And to undo multiplying by a minus g, we divide both sides by a minus g. So this gives us that the mass will be equal to the force of tension divided by a minus g. We could have actually also done that on a lot of these examples, like here, well, all of them actually. We could have pulled out the mass here or here. I didn't bother with it then because we knew the mass, so we could just put it in. But in this scenario where we needed to actually isolate mass, we needed to be able to do that so that we could just have mass times something instead of mass times something minus mass times something else. Okay, now we are good to go as long as we define our directions carefully. We know our upward tension will be positive, our upward acceleration will be positive, and acceleration due to gravity will be negative, 9.81. So the maximum safe tension is 2.5 times 10 to the 4 newtons. Our upwards acceleration is going to be 2.35 meters per second squared, and then we're going to subtract negative 9.81 meters per second squared, because that's a downward acceleration. So under these conditions where we're at our max tension, I'm getting that the mass would be 2055.9 kilograms, okay? And so to 3 significant digits, that would be 2.1 times 10 to the power of 3 kilograms. So if we were to accelerate that mass at that acceleration, we would reach our maximum possible tension. Any larger mass or any larger acceleration and our cable would snap, okay? But notice, once again, we started simple, right? Start with the basic idea, F net equals ma. F net is just the sum of the forces, right? You get specific to your problem here, where you add your actual forces in. All right, so go ahead and try this one out, at the very least before moving on, okay? And if you're feeling like you want a little more practice before you continue, these are good ones to try at this stage as well. Okay, we're now going to shift gears a little bit and start talking about pulleys. Still an application of Newton's laws, okay? But a little more to think about in terms of the forces and their directions. All right, so pulleys, they are a little weird to think about at first, okay? But ultimately, they actually just do a very simple thing. At least the simple systems we're going to study in Physics 20, they redirect a force, okay? So that's it. So for example, if we take a look here, right? We've got two masses attached by a pulley, and the pulleys we're going to study are always frictionless, so they roll very easily. We can ignore the friction in the pulley, okay? Now, this force of gravity from this mass is pulling it down. But because it's attached to this mass, and there's a pulley here, that downwards force of gravity is going to pull on this mass to the right. So what's a downwards force when we look here is actually a rightwards force from the perspective of this mass. And vice versa, this force of friction here is resisting motion to the left when we look over here. But if we think about it from this thing's point of view, that force of friction is going to be translated into actually an upwards pull resisting gravity. And that's all a pulley ultimately does. It takes forces acting on individual masses and redirects them so that they can act on other masses in our pulley system. Okay, so here I have time paused, right? But mass 1, you can see it would be feeling a force of gravity downwards. But because it's attached to mass 2 by a string and there's a pulley in between, mass 2 is going to feel a pull to the right as a result. So as mass 1 is pulled down by gravity, it pulls mass 2 along with it. Right now I have no friction, okay? So mass 1's downward force of gravity is a pull to the right for mass 2. And that force of gravity is now accelerating the whole system, mass 1 and mass 2. Now if I introduce some friction, right? It's the same scenario, except now we've also got friction up there at mass 2 that's going to be resisting the pull of gravity. And so what happens, it still accelerates downwards, but not quite as quickly because that force of friction is fighting the motion of both masses. So because of this fact, because these forces are redirected by pulleys to act in more than one axis, right? A downward FG in the y-axis, when we look over here, becomes a rightward force in the x-axis. It can get confusing if we try to stick with our usual focus on X and Y and splitting into components and things like our, up is positive, down is negative. Because this force here that's down, maybe we want to call that negative, but once we switch over to this mass, it's now to the right, which is in the x-axis and doesn't even have anything to do with up being positive and down being negative, right? That can get a little bit confusing. Like we said, the same FG that pulls the hanging mass downward is pulling the mass on the table to the right. And it's the same force, but depending where you look, it's in an entirely different axis. So you might be thinking, oh boy, that's complicated. How are we going to analyze that? We actually have a nice way to not work around it, but to kind of zoom out and think big picture, which actually makes it not too bad to analyze. So instead of getting too obsessed with this is one mass, this is a different mass, this is feeling forces, this is feeling forces, we recognize that really because they're connected, this is like one big thing. It's a big mass that has different forces acting on it, right? What we do is we look at the entire system without focusing too much on the individual masses when it comes time to calculate the net force acting on it and the mass that it's acting on it. We treat it like one big object because it really is one big object. It's all attached. And some forces are generally pulling in one direction and others are generally pulling in another direction. So if I look at this whole system here, right, I can kind of see it's like one big object and gravity's trying to move it that way while friction tries to resist it the other way, right? Now, since we're dealing with different axes and stuff going on, we can't do our usual up is positive, down is negative, left is negative, right is positive thing, right? So what we do is we say, since we're treating it like one big object where multiple things are going on in multiple axes, we just say that overall, whichever direction the system will move is the positive direction. So in other words, forces that are trying to make the system move will make them positive. Forces that are trying to stop that motion or resist it are negative. And that just simplifies things way down and still works perfectly well. Okay, so essentially what we do is we look at it like this. Generally speaking, this is one big object. And because the force of gravity is trying to pull it this way, we'll say that the system kind of has a general pull like this. That will be our positive direction, right? Anything resisting that, like friction, we'll call that the negative direction. So positive forces are anything that work towards moving the system. Negative forces are any that work against moving the system. Sometimes some students even like to just simplify it even further and say, hey, here's what we got. Yeah, they're connected by masses or by strings and with a pulley, but ultimately it's like one big mass, right? And in this one big system, we've got a force of gravity that's trying to move it one way, and we've got a force of friction that's trying to resist that, right? And we just simplify it down to that level, okay? So positive forces help it move, negative forces restrict motion. And this way, it doesn't matter which individual mass we look at, and we don't have to get too obsessed with our X or Y axes and our positives and our negatives. We just think about the system as a whole and whether the force contributes to or works against motion. And then you guessed it, we put it into A equals F net over M, where the net force is the force acting on the whole system, and the mass is the mass of the whole system. So all masses involved. Since they're attached, they're stuck together, they accelerate together. So they have the same acceleration individually as the whole system, right? It's like being on a bus that's accelerating with other passengers. You, all the other passengers, and the bus all have the same acceleration because you're part of one big system. Same idea here. Okay, so here's the breakdown of a lot of stuff we just talked about, right? Usually the force or forces that are pulling and trying to move the system, it's just the force of gravity of the dangling mass, right? Or masses, okay? F net is the total mass times acceleration. A equals F net over m, right? But F net is the net force on the whole system, all masses. Remember, we're thinking them as like one big object. M total is the total of all masses. That's the mass of the whole system because all of them are being accelerated by that net force, right? The net force is now accelerating the whole system. So that's the mass we need to think about accelerating. Again, A is the acceleration of the whole system, but because they're all attached, it's the acceleration of each individual mass too. And rope tension, when we get to some examples later calculating about the tension, it's actually only for the masses behind it because that section of the rope is only responsible for pulling those masses. We'll see that concept in action on one of our examples here, but let's start out with the first example. Okay, so again, we're going to think big picture. We don't want to get too obsessed with horizontal, vertical, 5 kilogram mass, 4 kilogram mass. We're going to look at this as one big object being tugged in one direction by some forces and maybe another direction by other forces. So if the table is frictionless, we want to calculate the acceleration on the 5 kilogram mass, the 4 kilogram mass, and the system itself. Well, hang on a sec. If we answer A, can B be any different? No, they're attached. Can C be any different? No, it's the whole thing is accelerating at that, right? So by answering A, we're automatically answering B and C. The only difference will be direction. Because as this mass accelerates down because of gravity, this will accelerate to the right because of that same force of gravity. Okay, so let's think about our system and the forces acting on it. Well, in this case, right, this force of gravity, which is just going to be the 4 kilogram mass times 9.81, is trying to accelerate the system, right? Generally, it's making it move like this, okay? There's no friction, so that's actually it, right? If you're saying, well, but this has a force of gravity too, true, you're right, but that's actually just going to be canceled out by the normal force because this thing is not accelerating up or down, right, off the table or into the table. So all that's trying to move the system is this thing's force of gravity. So big picture here, what do we have? We have a 9 kilogram mass, right? A 5 kilogram plus a 4 kilogram mass. And there's one force acting on that system. It's the force of gravity trying to pull it, in some direction. If you're here, that direction is down. If you're here, that direction is right. But overall, for the system, it's just being pulled how gravity is trying to pull it, specifically gravity from that mass. Okay, so the acceleration of the system is going to equal the net force on the system divided by the mass of the system. I'm just going to give these numbers. I'll call it 1 and 2. So that this is force of gravity from mass 2, okay? Now, the net force on the system is pretty easy here. It's just Fg2. So the acceleration of our system is just going to equal that force of gravity divided by the mass of the system. That's the only force acting on the system, and that's its mass, so we can find the acceleration, okay? Now, we know the mass of mass 2, it's 4 kilograms, so we can find what Fg2 actually is because the acceleration of the system then, right, Fg equals mg. So be very careful here. Only this mass is producing this force of gravity that's moving the system. So we just want to do mass 2 times acceleration due to gravity, right? But that force is now responsible for accelerating the whole system. So we're still dividing by the mass of the whole system. Okay, so remember, we're going to define the direction that the system would try to move or move as positive, right? So we just have to ask ourselves, does this force contribute to motion or fight motion for this system? Well, it contributes to motion. In fact, in this one, it's the only reason for motion. So we're going to call this positive, right? Positive is the direction the system will move or try to move. So that means when I put in my 9.81 here, I'm going to make it positive. Now that force is moving the whole system. So for my mass of my system, I need to do mass 1 plus mass 2. So 5 kilograms plus 4 kilograms. That is the one big object that we're moving's mass. So I got that the acceleration of the system is going to be 4.36 meters per second squared, right? Just finding that one mass's force of gravity and dividing by 9 kilograms. Now notice again, it's a little bit smaller. Well, it is smaller than 9.81, right? That's because this thing's force of gravity is now not just accelerating this mass, it's also accelerating this mass, right? We can see that here. We're taking the force of gravity acting on this, but dividing it by the total mass of the system. Because of them being connected, that's what that force of gravity is now trying to accelerate. But there we go. That lets us answer A, B, and C. So for A, the acceleration of the 5 kilogram mass, it's going to be accelerating that fast. And which direction will be accelerating? To the right, right, towards the pulley. Because as the gravity pulls this down, this gets pulled to the right because of the string and pulley. So we'll say for A to 2 sig digs, 4 meters per second squared. Right or towards pulley, both are fine here. For B, though, the 4 kilogram mass, it's the same magnitude. It's still 4.4 meters per second squared. The only difference is which way is this mass going to be accelerating? Down, right. And for C, the acceleration of the system, that's actually what we found. It's 4.4 meters per second squared. We can't give a nice, neat direction here because the system overall, right, it depends where you're looking. So all we can say is positive. It will accelerate in the direction that it accelerates. Okay, depending on where you look, that might be down, it might be right. But overall, the whole system is accelerating at 4.4 meters per second squared. So not so bad, right? Because we treat everything like one big mass with forces pulling in one direction or another, it actually simplifies quite a bit our analysis here. Okay, let's try one now where there is friction. So if the acceleration of the system is 1 meter per second squared, we now want to calculate the force of friction. Okay, so we've got, if we take a look here, right, again, what's going on? Well, if I call this mass 2, the force of gravity from mass 2 is what is moving the system, right? But we know that there is a force of friction resisting that pull, and it will be there, right? So big picture, again, thinking about this as one kind of big object, which it essentially is because it's all attached together, right? If you like drawing out the simplified version, what we've got here is a 9 kilogram mass. And generally speaking, that force of gravity is trying to pull it one way, and friction is resisting that pull. The only reason it looks more complicated is because this pulley is acting to redirect the force from here into another axis. But generally speaking, that's all that's going on. So as always, start general with the basic principle, okay? And then we can get more specific to our problem. So we want to calculate the force of friction. So I'm going to solve this for F net. So F net equals MA, okay? But F net now has more than just the force of gravity. There's also the force of friction. So F net is that force of friction plus that force of gravity. Just the force of gravity from this mass, right? Fg2, if I'm calling that mass 2. Okay, now before I go any further, we should think about signs and directions, right? Anything that is trying to move the system is positive, okay? So these will be positive. Anything that is resisting that will be negative, right? So looking down here on our simplified version, what's going to be positive, what's going to be negative? Well, this is trying to move the system, so we will treat this as a positive force. Friction is resisting that motion, so it will be negative, okay? At least we're predicting it will be. That's what we're trying to find. So let's isolate the force of friction here, right? And now we're ready to plug in, recognizing that Fg2 is just going to be mass 2 times 9.81. And again, we're going to make 9.81 positive here, right? This is just this mass times 9.81. That's how strong that force of gravity will be. So the mass of our system, once again, is going to be 9 kilograms, 5 plus 4. We're told that this system accelerated at 1 meter per second squared. Hey, question for you, positive or negative? Positive, right? It's accelerating in the direction it got pulled, it got moved. We define the direction the system will move or try to move as the positive direction, so positive 1. And then we're going to subtract m2, so 4 kilograms, times a positive 9.81 because gravity is helping it move here. It's not working against the motion. It's actually the entire reason for the motion. So paying careful attention to my signs there, doing that math, I got that the force of friction must be negative 30.24 newtons. Now, negative, is that a good sign or a bad sign for us here? That is a very good sign, right? We said friction should be negative because we're defining the direction of system motion as positive. Friction is working against that, so it should be negative. Okay, and so to two significant digits, we could say 30 newtons, and direction here is a little tricky to say, but the best we could probably do is say against the motion, right? Resisting motion, or away from the pulley could also work, something like that, right? But again, the direction friction looks like here is totally different than what it looks like from this mass. So typically we just want to be general with these. And there we go. All right, so in this next one, things are a little more interesting, but don't get overwhelmed. It's the same principle here, okay? Yes, we've got 3 masses, but they're all connected together, so we can kind of treat them like one big object with certain forces pulling in one direction and other forces pulling in another direction. So we're assuming a frictionless surface here. Let's just think about the forces that are therefore going on. Well, we've got these 2 hanging masses, right? I'm just going to give them numbers so we can talk about them. Let's say 1, 2, and 3, okay? Mass 1 is going to feel a force of gravity that pulls it like this, right? We can call that Fg1. And because it's pulling on this one, it's also pulling on this one and on this one. It's pulling the whole system with that force. But over here on the other side, we've got mass 3, which is also going to have a force of gravity. And it's going to be larger because this is a 2 kilogram mass and this is only a 1 kilogram mass. And again, there's no friction here, so this is free to slide, right? It's kind of caught in a tug of war between this force of gravity and this force of gravity. In fact, the whole system is actually just caught in a tug of war between those 2 forces of gravity, right? Fg1 is kind of trying to pull the system that way. Fg3 is trying to pull the system that way. Reminder again that yes, mass 2 does have a force of gravity, but it's not that relevant to the overall system here because it is just being canceled out by a normal force from the table. So if you'd like to kind of visually simplify and think about one big mass, right, what we have here is a 1 plus 1 plus 2 kilogram mass, right? 1 plus 1 plus 2 kilograms total is the mass of our system. And it's being pulled one direction by Fg3 and then actually in the opposite direction by Fg1, right? And there we go. We've simplified this down. That's really big picture. That's what's going on here. And so we can just go ahead and say that the acceleration of this system is going to equal the net force acting on the system divided by the total mass of the system. Net force, like always, is the sum of all forces. Well, in this case, we've just got Fg3 and Fg1. As always, though, got to be careful about signs here, right? So the convention is to define the direction that the system will move or try to move as the positive direction. So which way is this system going to move? Is Fg3 going to win or is Fg1 going to win? Right, Fg3 is going to win. In this case, because it's a larger force, right? This is 2 times 9.81. This is only 1 times 9.81. So we're going to define this direction as positive. So it seems a little odd maybe at first, but it is possible in a question for gravity to be positive 9.81 for one force and then negative 9.81 for the other force. But that makes sense because from the system's perspective, these 2 forces of gravity are in opposite directions, right? They are tugging the system in opposite directions. So let's break these down. Fg1 is of course going to be mass 1 times 9.81, and FG3 is going to be mass 3 times 9.81. I'm going to make this one positive because this one is trying to move the system, and this one is actually resisting the direction the system will move. And so for FG1, I'm going to make it negative 9.81. Okay, now the mass of our system is just, well, M1 plus M2 plus M3, right? That's the mass of the whole system. All right, I think we're ready to plug in our numbers. So mass 1 times negative 9.81 plus mass 3 is 2 kilograms, and that's going to be positive 9.81 meters per second squared. Again, this makes sense. These two forces have opposite signs now. They're canceling each other out, which makes sense because as far as the system is concerned, they are fighting each other. They're working against each other. Okay, divided by the total mass of the system, which is just 1 plus 1 plus 2, right? Or 4 kilograms total. So putting that all in my calculator, being careful about signs, I would recommend breaking this down into steps, okay, as you enter on your calculator. But I got that the acceleration of the system would be 2.4525 meters per second squared, okay? Best we can say is positive because, again, we're thinking about the whole system all at once, right? Saying up or down doesn't really make sense because depending on which mass within the system you're looking at, that can be totally different, right? This one's going to be accelerating down, but this one's going to be accelerating up, right? And this one's going to be accelerating to the right. So best we can do is just say positive 2.5 meters per second squared. That overall is how the system will be accelerating. Which direction depends on which mass individually you look at. All right, so pause the video, try this one out for sure, okay? And then it's also a good time if you'd like to do a little more practice now before moving on to just, we only have one example left, but you could also try those ones out. All right, now we'll return to this example here, which was the one I mentioned earlier, where we will see what happens when we need to think about the tension in a certain part of the rope. Okay, so when these problems arise where we're trying to find the tension in a particular section of the rope, big picture, nothing changes. For thinking about the acceleration of the system and the net force on the system, we're still thinking about it as one big object. Now, the net force does act on the whole system, okay, but it's actually individually spread out between the masses, right? Not all of the net force acts on the 1 kilogram mass or the 2 kilogram mass or the 3 kilogram mass, but it's spread out, right? Yes, the whole net force acts on the whole system, but a portion of the net force is kind of divided between the three masses. And that's where the tensions in the individual sections of the rope come in. Because the portion of the net force that is responsible for accelerating the 1 kilogram mass is just this portion of rope, right? Notice if I were to cut that rope, right, the 1 kilogram mass would just sit there and this would be our system, right? So it's actually that rope is only responsible for accelerating the 1 kilogram mass. It carries a portion of the F net in order to accelerate the 1 kilogram mass. It's not the entire F net because that section of rope is not doing anything to accelerate the 2 kilogram or the 3 kilogram mass, right? There's a larger portion of F net in this section of rope because it's responsible for accelerating both the 2 kilogram and 1 kilogram mass, right? If I cut that, then the 3 kilogram mass just falls and those two don't do anything. So that idea is the key to understanding these tension problems, right? We just have to think about, first, big picture, F net on the system divided by mass of the system will give us the acceleration of the entire system, right? But then to focus in on tension in a particular section, we have to think about what mass that section is actually accelerating, because that will tell us how much force it's carrying as tension. So in order to find the force that's acting on it, in other words, the tension in this rope here that's acting on just this mass, right? Well, what we can do is find the acceleration of the whole system, like we always would, because we know since they're all attached together, that's the acceleration of this mass. And then if we divide by just its mass, right, instead of the whole system's mass, we can figure out the force, the tension that is in this rope carrying it, right? If we have the acceleration of this mass and we know its mass, we can figure out what force would cause that acceleration for that mass alone. So there's our plan. First, we're just going to find the acceleration of the whole system because that is the acceleration of this mass as well. I'm just going to give them numbers here. We'll call it mass 1, mass 2, mass 3, right? So therefore, we're finding the acceleration of mass 3 because it's part of the system. It has the same acceleration as the whole system. So just like before, the acceleration of the system is equal to the net force acting on the system divided by the mass of the system. And since there's no friction, the net force acting on this system is just the force of gravity from mass 1, right? So F net is just Fg1, and the mass of the system is just, well, m1 plus m2 plus m3. Okay, and Fg1 is just mass 1 times g, acceleration due to gravity. I'm going to make it positive because that's the direction the system is trying to move. So I'll put a positive 9.81 in there. We've got a 3 kilogram mass, acceleration due to gravity 9.81 meters per second squared, divided by 3 plus 2 plus 1 kilograms. So that gave me that the acceleration of the whole system, and therefore the acceleration of each mass in the system, was 4.905 meters per second squared. Now, think about this from mass 3's perspective, right? As far as it's concerned, what's happening? Well, this rope is pulling it to the left, right? That is a force of tension, okay? And that force of tension is causing it to feel this acceleration, right? It's not the entire net force. Remember, that's spread out between all of the masses, okay? But for just this mass, it's just this much tension pulling it that way. So we know how big of a mass is being accelerated by this force, and we know how big the acceleration is. Well, if we know a mass and that mass's acceleration, we can find the force that's causing that acceleration. Because the acceleration of mass 3 will equal the force on mass 3, right? So you could call it F net 3 if you like, divided by mass 3, right? Got the acceleration big picture, and now zooming in on one of the masses to think about what that means, how much force was acting on it, right? Since there's no friction, F net on 3 is just this force of tension in this section of rope alone. So that force of tension that we're interested in is just going to be equal to mass 3's mass, which is 1 kilogram, times its acceleration, which is the same as the acceleration of the system because it's part of the system. And therefore, the force of tension is going to be 4.905 newtons, okay? Or to two significant digits, that would be 4.9 newtons. And we could say to the left or towards the pulley because of the diagram they've given us there. But there we go, right? Notice that's not the whole net force. Again, it couldn't be the whole net force because if that much force was acting on just a 1 kilogram mass, its acceleration would be a lot bigger than 4.905, right? It would be 1 kilogram times 3 times 9.81, right? So we can tell that that total net force on the system is not acting individually on each mass, right? It's spread out individually. So we just found the portion of that net force that is responsible for accelerating this 1 kilogram mass here, okay? It's the tension in that rope. All right, there we go. That's the last example for this lesson. So you can pause this video and now do part B of the question you just did, which talks about finding the tension in the rope, okay? But after that, you're good to complete whatever practice problems you haven't done throughout the lesson. And as always, make sure you're reaching out for help, send an email, book a meeting, right, as needed. I'm always happy to help out however I can.